Hi, I am Sridhar Chitta. In a set of two videos, I shall discuss the design and operation of a regulated DC power supply using a unified approach to electrostatics in circuits. I express my sincere thanks to Professor V. Kamaraju, retired Principal and Professor, Department of Electrical Engineering, JNTU College of Engineering, Kakinada, Andhra Pradesh, India. In this video, part 1, I shall describe the construction and operation of a step-down transformer, AC to DC rectification featuring a bridge rectifier, the construction and operation of a capacitor used as a filter, and the generation of an unregulated DC voltage. And in the video part 2, I shall discuss the salient subassemblies in a regulated power supply, including the operation of the series pass transistor and the means of controlling the voltage drop across the series pass transistor and also overall regulator operation. The astounding speed of operation of the voltage regulator when making adjustments to counter voltage fluctuations is quite amazing, and this I have indicated towards the end of the video before I conclude with an overview of an integrated circuit fixed voltage regulator. The animations in the video are useful as an aid to visualize the circuit processes in the operation of the regulated DC power supply. We have not shown the surface charges that are present which enable the conduction processes in the components for the sake of clarity. It is recommended that the viewer refer to the two videos 1 and 2 listed in the references at the end of this video part 1 of 2, which provide a comprehensive description of the role of surface charges in enabling conduction in electrical and electronic circuits. A DC power supply is an important requirement in almost all electronic systems like televisions, stereos, and computers, and in medical, industrial, laboratory, and military electronic equipment. A DC power supply contains the following major circuit component subassemblies: a transformer, a rectifier, and a filter. We will now describe the design of a DC power supply of 25 volts which uses 230 volts AC mains as its input. A transformer is used to step down the input mains 230 volt AC to about 25 volt AC. It typically consists of punched steel laminations riveted together to form the core of the transformer. The purpose of laminating the core is to reduce the eddy current loss. The primary and the secondary coils are wound using copper wire on two legs of the transformer. The copper wire used to make the coil is coated with varnish so that each turn of the winding is insulated from every other turn. Note that since the transformer is a step-down type, the primary coil has more number of turns than the secondary coil. When the secondary is on open circuit, its terminal voltage is the same as the induced EMF, and V2 divided by V1 is approximately equal to N2 divided by N1. The wire used to make the primary and secondary coils is insulated copper wire and is also called enameled wire. Enameled wire is a wire coated with a thin layer of insulation to prevent the wire surfaces from being in a short circuit when wound into coils. Magnetic flux is created when current flows through the coil. Coiled wire bundles find use mainly in the construction of motors, electromagnets, transformers, and inductors. The coating or enamel used on wires is sometimes colorless and transparent, and so it is hard to detect this visually. However, a meter can be used to check continuity, and the lack of continuity will confirm the presence of the coating on the wire. Transformer operation is based on two principles. First, that an electric current can produce a magnetic flux, electromagnetism, and second, that a changing magnetic field within a coil of wire induces a voltage across the ends of the coil according to Faraday's law. Changing the current in the primary coil changes the magnetic flux that is developed. The changing magnetic flux that also changes direction clockwise and counterclockwise based on the winding sense every half cycle induces a voltage in the secondary coil that also changes polarity every half cycle. According to Faraday's law, a Curly pattern non-Coulomb electric field co-occurs with a changing magnetic field. The non-Coulomb electric field polarizes the secondary coil and this produces a Coulomb electric field. This explains the experimentally observed. Watch the videos 1 and 2 listed in the references at the end of this video. Unification of electrostatics in circuits, and this is how an induced EMF is observed across the ends of the secondary coil. This is not discussed in most textbooks of electricity and magnetism. For a full and comprehensive discussion of the co-occurrence of the Curly pattern non-Coulomb electric field, the viewer may refer to the textbooks 3 and 4 listed in the references at the end of this video. The core laminations serve to confine the magnetic field and strengthen the flux density. Note how the changing magnetic flux induces a voltage in the secondary coil. The voltage in the secondary of the transformer is a smaller voltage than the voltage applied to the primary because there are fewer turns of the secondary that link with the changing magnetic flux produced by the primary coil. There are other constructions for transformers. Since a magnetic field, like an electric field, penetrates through matter, the coils can be wound one over the other. When the primary winding is completely wound, it is wrapped in insulating paper or cloth. The secondary winding is then wound on top of the primary winding. After the secondary winding is complete, it too is covered with insulating paper. Next, the E and I sections of the iron core laminations are inserted into and around the windings and the laminations riveted together. The image shows the finished construction of the transformer. In yet another construction seen in this photo, the windings can be sandwiched one above the other around the central limb. The image is of a typical commercial step-down type small transformer for low power applications to provide low voltage AC in consumer electronics and small electronic gadgets. We usually avoid drawing the transformer core in the form of laminations in circuit drawings and prefer to show the core with a few closely spaced vertical lines for the sake of clarity. The transformer is used to step down the input mains voltage 230 volt AC to about 25 volts AC. A bridge rectifier that uses 4 diodes is used to convert the secondary AC voltage to DC, and it produces a pulsating voltage at the output of the rectifier and across the load resistor. A blue line is used to show the path of the current during the positive cycle, and a green line is used to show the path of the current during the negative cycle. A diode allows current in one direction and prevents the flow of current in the reverse direction. For a description of diode operation, refer textbooks 3, 4 and 5 listed in references at the end of this video. Note that in the bridge rectifier, one pair of diodes conducts during the positive cycle and the other pair during the negative cycle. The rectifier is also called a full wave bridge rectifier because it produces a pulsating voltage at its output utilizing both half cycles of the voltage at the secondary of the transformer. The output of the rectifier is not a steady DC voltage and it has a ripple. The output of the rectifier that is applied to the load is a pulsating voltage and contains ripples. The ripples can be minimized and the output made less fluctuating or steadier by using a filter that removes high frequencies. The filter consists of a capacitor. In the two textbooks 3 and 4 listed in references at the end of this video, the process of capacitor charging and discharging is described using a unified approach to electrostatics and circuits. Textbook 4 includes descriptions of the currents in capacitors and CR circuits when subject to sinusoidal voltages at various frequencies and how capacitors are used as filters. A large capacitor, when connected across the load resistor, bypasses high frequencies and therefore has the ability to remove ripples. A steady DC voltage of about 25 volts or more is produced. The price for removing ripples is the current peaks in the transformer windings, conducting diode pair, and the capacitor, which is used to bypass high frequencies. The filtering capacitor, the output, does this by storing energy in the form of displaced charges on its plates and maintaining a reasonably steady voltage across it without discharging too quickly. With the intention of storing more energy, if the size of the capacitor is increased arbitrarily, the P current in the diode will also increase, and this may cause the diode to heat and eventually burn out. See the topic Diode Conducting in section Capacitor Filters in the chapter Application of Diodes in textbook 5 listed in the references at the end of this video. There are other types of filters too that may be used. An inductor filter consists of an inductor connected in series with the load. Its action is to oppose any change of current, and so any changes that may occur in a circuit without an inductor are smoothed out by the presence of the inductor. The action of the capacitor and the inductor filters may be combined into a single L-section filter. The increase in ripple with increasing load of the shunt capacitor and the decrease in ripple with increasing load of the series inductor combine to provide a steady voltage against sudden current changes in the load. For more details, refer to the section L-section filter in the chapter Application of Diodes in textbook 5 listed in references at the end of this video. The image shows the construction of a rolled foil and a ceramic disc capacitor. A capacitor usually consists of a sandwich of two metal foils separated by insulating material and coiled into a small package. The image shows the construction of an electrolytic capacitor that is usually used as a filter capacitor in power supplies. A DC power supply works reasonably well under most circumstances, providing a fairly steady voltage that can power several circuit applications. However, there is one major drawback in its operation that does not permit its use in applications where the input voltage may fluctuate and when there are large load current requirement swings. If the input voltage mains is normal, the DC output voltage will satisfy design requirements. If the input voltage mains were to increase, the secondary voltage of the transformer will increase. The DC output voltage will also increase. If the input voltage mains were to decrease, the secondary voltage of the transformer will decrease. The DC output voltage will also decrease. A DC power supply works reasonably well and can power several circuit applications. However, if the input voltage fluctuates and if there are large load current requirement swings, it will hamper the operation of critical electronic circuits, and therefore some means to regulate the output voltage becomes necessary. In part 2 of this video set, we will learn how an electronic circuit is used to regulate the voltage within reasonable limits of swing of the input voltage. See the description below this YouTube video for a link to part 2 of this set of 2 videos.